So we've got this loop of circuit. We've got a battery, capacitor, resistor. At time 0, we're told that the charge is 0.12 coulombs, so we can convert that to a voltage by using charge over capacitance, and we get 1.2 volts. So 1.2 volts of voltage on the capacitor at the beginning. And ultimately, we're trying to graph this. So if we try setting up a graph of voltage versus time. Time versus voltage. And strictly speaking, this should be delta V, because we're talking about the difference in voltage from one side of the capacitor to the other. We know at the beginning it's 1.2 volts. So let's mark that on the graph. And after a long time, again, we're expecting the current to be 0, because after a long time, everything has settled down to its new final equilibrium. The capacitor will eventually be as full as it's going to get, because the capacitor is pushing back against the flow of charge. So at that point, if the current is 0, it might help to set up the loop rule equation here. If we write out the sum of all the voltage differences equals 0, what would we have to include in the delta voltage equation here? If you start at some location, go all the way around the circuit, what voltage differences are you passing through? Yeah, we got the capacitor, IR from the resistor, and the battery itself. So if we write that out, delta V battery plus delta V capacitor plus delta V resistor equals 0. Then we should be able to fill in a delta V formula for each one of those. Battery is just going to have a constant voltage plus epsilon. Capacitor is going to be negative Q over C in general. And resistor is going to be negative IR. Those are the general formulas for each of those circuit elements. And specifically, if we know that after a long time, the current is 0, what happens to this resistor term? Yeah, well, R is not 0. R is still 10 ohms. Why was which delta V? Do you mean the sum of all the delta V's? This is usually called the loop rule, and it should be true for any complete loop. Like in general, if you start at some location, that location has a voltage associated with it. If you start moving around the circuit, like going through the battery increases your voltage, going through the capacitor causes some change in voltage, going through resistor causes some change in voltage. But if you get back to the starting location, you've returned to the starting voltage as well, because this location just has one value for voltage. So that means in a complete loop, the sum of all the delta voltages you encounter has to be 0, because you return to the starting value. And that's usually called the loop rule or the Kirchhoff's voltage law. So that's true for any time you're talking about a path that forms a complete loop. No matter what the path is, as long as you start and end at the same location, the sum of all the delta voltages you encounter has to be 0. There is one exception to that. If there's a changing magnetic field, we'll get to that in 7C. But for now, no magnetic field's changing, so we can assume that all the voltages in the loop add up, all the voltage changes in the loop add up to 0. And if the current is 0, it doesn't really matter what the resistance is. Current equals 0 times any resistance is going to be 0. So after a long time, when the current is 0, this term is gone. There is no delta voltage in a resistor if there's no current flowing. What does that tell you about delta V battery and delta V capacitor? Yeah, they've got to be the same. Strictly speaking, they'll be opposites. We would say delta V battery is plus epsilon, delta V capacitor is minus epsilon, but at least its absolute value will be the same. Its magnitude is the same. So that means after a long time, the capacitor's voltage will be the same as the battery, 1.5 volts. We label that delta V capacitor. Delta V capacitor will match the voltage of the battery. Because there's no current. I guess strictly speaking, we should probably call that negative 1.5. It does say be careful of signs, so we probably want to do that. I would call this negative 1.5 volts because it's if you go in the loop around the circuit like this, we're going from a high voltage zone to a low voltage zone. And notice this is true even at the beginning. At the beginning, we got 0.12 coulombs of charge with positive on this plate and negative on this plate. So if we go through this clockwise loop, we're going from the high voltage zone, the positive plate, to a low voltage zone, the negative plate. So I think we should probably call that negative as well. So let's go ahead and put the time axis up here and call this negative 1.2 volts. And we also know after a long time, the delta V of the capacitor will be negative 1.5 volts. So let's mark that on our graph as well. We now at least know the starting value and the asymptote. We know that at the beginning, the voltage is negative 1.2 volts. And we know after a long time, it should approach an asymptote of negative 1.5 volts. So that's the asymptote it'll be approaching. And what shape should it look like between those? What kind of graph is this? Yeah, we should expect exponential decay here. Starting off changing quickly because at the beginning we've got a fast current. And then leveling off towards the asymptote as the current gets slower and slower, because the rate of change then gets slower and slower. So I would expect the graph to look something like this. Any questions on that so far? It also says to label the time constant. And we found earlier the time constant is 1 second, because time constant in the case of a simple loop like this with one resistor and one capacitor, time constant is always going to be resistance times capacitance. So 10 ohms times 0.1 farad is 1 second. What does that mean though? Time constant is the amount of time it takes for what to happen? To decay, specifically to decay how much? It's about 37%. There's nothing really special about 37%. It's specifically 1 over E of the original amount. The time constant is the amount of time it takes to decay to 1 over E of the original. E just being a convenient reference point because we're writing our equations in base E to the power of something. Specifically though, it's not the 1.2, the negative 1.2 volts isn't what's decaying though. What's decaying is the difference between the value and the asymptote. So if we take a look at how different the value is from the asymptote, Like for instance, at the beginning, how far is the value from the asymptote? What's that difference at the beginning? Yeah. Or since we're talking about above the asymptote in this case, I'd call it positive 0.3. So at the beginning, at time 0, we are 0.3 volts above the asymptote. That's the value that's decaying. Because if you take a look at what's happening as time passes, the important thing is the difference with the asymptote is what's getting smaller and smaller and smaller and smaller. So that difference is what's shrinking as time passes, regardless of the actual value. For the time constant, we're looking for how much time it takes for the 0.3 volts above the asymptote to decay to 1 over E of 0.3 volts above the asymptote. So after 1 second, this decays to 1 over E of 0.3 volts above asymptote. And we can punch that into a calculator. 0.3 volts divided by E, 0.3 divided by E is about 0.11 volts. And so we can run that calculation as well. 0.11 volts above negative 1.5 would be negative 1.39. Because that's 0.11 volts above negative 1.5. That tells us after 1 second, the voltage on the capacitor should be negative 1.39 volts. Because that's 0.11 volts above the asymptote, which is 1 over E of the original difference, 0.3 volts. So if we mark that on the graph as well, let's put a mark at negative 1.39. Which will be about here. I'm just estimating here. We'll probably want a more accurate graph if you have some graph paper available. But about here, let's label that negative 1.39 volts. That location is going to be the location that represents time 1 second. So right here, the graph passes the negative 1.39 volt mark. That time on the time axis should be the time constant, which we know is 1 second. And then if we go to 2 seconds, that's another half-life. So we'll decay to 1 over E of that. We take the 0.11 volts, divide that by E, and will then be that high above the asymptote. And you can keep dividing that difference by E every 1 second further into the future you go. Any other questions on that so far? Also, can we figure out how much charge there is going to be after a long time? Because we're going to need that for part B as well. We know the final voltage after a long time is 1.5 volts. How would we convert that to a charge? Yeah, we can multiply by C because once again, delta V for a capacitor is charge over capacitance with a negative sign, but we can think of this in terms of absolute value for now. So if we take that voltage and multiply by the capacitance, 1/10, that gives us 0.15 as the charge. So the voltage times the capacitance will tell you how much charge it stores at that time. So that gives us some information we can use for part B. If we're trying to write an expression for charge as a function of time, we know we start with 0.12 coulombs of charge, and it's going to approach 0.15 coulombs of charge. And it might help to draw out a graph of that as well. If we're going to be making a function for it, we may as well draw out a graph of what we expect this to look like. We know we start at 0.12 and we're approaching 0.15. Some more space here. So we're starting, and this is a time versus charge graph. We know we start at 0.12 coulombs, and we're going to approach an asymptote of 0.15 coulombs. And this is also going to be exponential decay. That, as far as charge is concerned, we start at 0.12 coulombs, and we're going to approach an asymptote of 0.15 coulombs. Any questions on that so far? So let's see if we can write a function for this. Charge as a function of time. First of all, this is exponential decay, so we should expect this to include e to the something. How would we decide what exponent to use, though? The e to the whatever. How do we decide what that whatever is going to be? Well, the thing is, it's going to have to involve time. This is a function of time, so this is going to have something to do with t. But the thing is, the exponent needs to be unitless. You can't have like e to the power of 5 kilograms or e to the power of 3 seconds. It's got to be e to the power of a number, completely raw, just a number, no units of measurement at all. What units of measurement is t measured in? Yeah, t is measured in seconds. So to cancel that out, we're going to have multiplied by something in units of 1/seconds, or divided by something in units of seconds. So and typically what we're going to do is we're going to take time divided by some specific amount of time. And what's the only specific amount of time we really care about here? What's the only specific amount of time that's really relevant to an exponential decay situation? The half-life, the problem is half-life isn't related to E. Half-life is what we would use if we were writing this as 2 to the power of t over something. But what other amount of time is specifically related to the number E? What amount of time have we just been working with that's related to the number E? Yeah, the 1 second, that time constant. And that's exactly what we need here. The exponent is going to be time, like what time it is right now, divided by the time constant. That way, seconds and seconds cancel out, so we get a unitless quantity. The exponent is essentially what time it is now as a fraction of the time constant. Like, for instance, if the time that has passed so far is 2/3 of a time constant, then that time divided by the time constant is just 2/3. We also need a negative here because we're talking about exponential decay. If this were positive, we'd have an exponential growth situation instead. So e to the power of negative time over the time constant should do it. That gives us the negative sign tells us this is exponential decay. Dividing the time by the time constant scales it to the right rate of decay. It makes it decay in the correct amount of time. So negative t over 1 second should work in terms of getting the right decay rate. The problem is, though, we also need to make some modifications, because if we just have e to the power of negative t over something, that starts at 1 because e to the 0 is 1 and decays towards 0. We don't want it to decay towards 0, though. We want it to decay towards what value? What should the asymptote be here? Yeah, we want it to decay towards 0.15 coulombs. How do we change? How do we make that change? If you have a graph that decays towards 0, but you want to shift it so it's decaying towards 0.15 coulombs instead, what could you change about the function that will shift the graph up 0.15 coulombs? Yeah, if we just add 0.15 coulombs, that should do it. So e to the power of the time constant plus the value of the asymptote. In this case, 0.15 coulombs. So that gives us e to the power of negative t over 1 second plus 0.15 coulombs. However, we also need one more modification, because the e to the power of negative t over time constant, if you fill in 0, you're going to get 1 plus the asymptote. And we don't want the value to be 1 away from the asymptote. We want it to be specifically how far below the asymptote. Because if you were to just fill in, yeah, we want it to be 0.03 below the asymptote. That means this function as it currently stands won't work. Because if you fill in 0 for t, what's e to the 0? Yeah, and we don't want 0.15 coulombs plus 1. We want 0.15 coulombs plus negative 0.03. So one way to do this is to put in a multiplier here. Let's say a times this. Fill in the initial conditions. You know that when time is 0, charge is 0.12. So fill in 0 for t and 0.12 for q, and then you can solve for what that a multiplier has to be. But it's going to turn out that that a multiplier is just describing how far above or below the asymptote the initial value is. The initial value is 0.03 coulombs below the asymptote. So that means this multiplier will be negative 0.03 coulombs. So this should work. And you can check by filling in some values. If you fill in 0 for t and find q, you should get 0.12 coulombs. If you fill in a very large number for t, like a million or something, this should result in 0.15 coulombs, or very close to 0.15. But this format should work. You've got an initial difference times e to the power of negative t over time constant plus the asymptote. But keep in mind, this isn't something to memorize. This is something to build. The main thing you need to know is that you start with e to the power of negative t over time constant to get the rate of change right, and then modify that to build the graph you're trying to create. Any questions on that function? And in general, if you want to get some more practice with this, it's fairly easy to just make up some exponential decay graphs. Like just start a graph, mark an initial value and an asymptote, draw a curve that starts at that initial value and approaches that asymptote, then try writing an equation to match that curve. Anyway, I've got to get going a little early to get ready for a final review session for another class, but try out some more practice. Yeah, I'll post the recording online. Let me know if you have any other questions for the review session tomorrow, and I'll see you then.